Okay, for our project, we decided to model a thermal system. This basically is a representation of a workshop, and the purpose is trying to keep it warm through the winter time. So what we have is basically this is a hot box that needs to be at a higher temperature for doing some curing, and the heat source, which is a kerosene lighter lantern, is inside of the hot box. This basic representation of the outer shed, and then a temperature sensor inside to turn the heater on and off. So what we figured for the resistance values for the walls was the hot box itself is basically an R3 value. The outer shed between the inside and outside the walls is has a rating of 13, and the temperature sensor itself has a rating of 1, which we got from basically just silicone. The heater itself puts out 6,740 joules per second, and we also calculated the capacitance values to be 1.44, 27, and for the sensor a value of 0.7. Okay, so for this project, for this control system, specifications that we had in mind were an overshoot value of less than or equal to 4%. We wanted the rise time to be as small as possible. The settling time in this case isn't applicable. We wanted our T2 to end up being 70 degrees, and our steady state error, we wanted a value of less than or equal to 1 degree.
Okay, so the reduction of the system that we have into a circuit model looks like this, where we have T1, the temperature inside the box here, T2, the temperature inside the room here, and Tm, the temperature inside the temperature sensor, the actual reading of the temperature sensor. And then we have it with reference to the outside temperature, which in our case we left at 0, just for a really cold day. C1 and Q dot are the capacitance inside the hot box and the heat flow coming in from the heater. R1 is the resistance between the inside of the box and the outside room. R2 and C2. R2 is the resistance between the room and the outside, and C2 is the capacitance between the capacitance of the room. R3 is the resistance value between the room and the inside of the temperature sensor, and Cm is the capacitance of the temperature sensor. And just basically using nodal analysis, we come up with these 3 equations here. For the first two, T1, T2, T3 there's no terms, T1, T2, and Tm, all 3 terms, T2 and Tm for the third equation, and then just solving this in MATLAB with matrices comes out with a really big function with big numbers in it for T2, the temperature that we're interested in. So dividing the big numbers out in front of the s cubed term, we get this transfer function here, which is 58s plus 8 over s cubed plus 1.7 s squared plus 0.4 s. And that there is a little bit of rounding in there just because it's not going to be exactly accurate.
Okay, so for our block diagram, after our analysis in MATLAB, here with the transfer function, we were able to come up with a K value of 0.02, which would give us zero overshoot for our design.
This diagram shows the root locus and the Bode plot for the open and closed loop systems uncompensated. This diagram shows the phase margin and the gain margin for the uncompensated open loop system. This diagram shows the uncompensated step response. Notice the sinusoidal response. This diagram shows the compensated response for the system. This diagram is the control signal of the compensated system. This diagram is the compensated output from the Q input to the temperature 2 in the shed. And this diagram shows the entire plant response with this 6,000 joule per second heater.